Howdy, my name is Vaibhavi, and me and my teammate Reshma will be going over this presentation, which is on the paper based on synthesizing formal models of hardware from RTL for efficient verification of memory model implementations. This sounds like a lot of words here, but essentially we're just trying to synthesize some formal models. We are doing that from hardware, like we're doing that for RTL, and we're doing that so that we can efficiently verify memory model implementations. And we're going to look at what this exactly means. This paper was in affiliation with Stanford and ARM, and these are the authors of this paper. And the conference was Micro 54. Let's start with the introduction. Memory consistency models, they govern how memory operations, reads and writes are observed across a processor, ensuring correct execution in parallel computing. They govern the visibility of writes, ensuring correct program execution. And modern processors, they feature a bunch of sophisticated optimizations like out of order processing, speculative execution, caching, and this makes MCM enforcement and verification highly complex. And the verification challenge here is ensuring that the processor's microarchitecture adheres to its MCM specification, and this is non-trivial. So bugs in these MCM implementations can lead to subtle or hard to detect errors. The existing solutions are formal verification techniques such as check tools, but they require manually written microspec models, and this process is tedious, it's time consuming, not to mention it being error prone as well. And this requires deep expertise in both hardware design and formal methods. So, which here or the goal here is to automate the synthesis of microspec models directly from RTL, and this just completely eliminates manual modeling overhead. This enhances efficiency and accuracy in MCM verification. Now we are going to look at some MCM models in the multi-core processors. These are the ones used widespread in academia and industry. So the first one is sequential consistency, which is the strongest and the most intuitive model. All memory operations appear to execute in global total order, and this order is consistent with program order. If you look at this example where x is equal to 1, r1 is equal to y in thread 1, and y is equal to 1, r2 is equal to x in thread 2, this violating this would indicate an out of order memory execution. So if R1 is equal to 1, then R2 is equal to 1 as well, because anything else would indicate an out of order execution, which is not allowed under sequential consistency. So this is the simplest model. It is not really used in any real world processor because of how simple it is. Another model is total store order, TSO, which allows store buffers. So this is also like sequential consistency, but stores can be now delayed in store buffers. This causes loads to read stale values. So the allowed outcome here can be, for the same example we saw earlier, R1 is equal to 0, while R2 is equal to 1 is possible because the thread 1 store is buffered and it's not even visible to thread 2. And this model is used in x86 or Spark processors. Another model here called weak ordering has fewer constraints but more parallelism. So operations are not required to follow program order except for explicit synchronization with the help of memory fences. So if a processor does not enforce ordering, a load could be executed before a prior store, and this would violate the expected behavior. So the solution here is just to use mfence. So that would ensure stores are visible before subsequent loads execute. The last model we'll be discussing is called release consistency, RC model, and this uses acquire and release semantics, or you can call them primitives such as lock, unlock, and this dictates when memory operations must be visible to other threads. And sorry, the example here shows two parallel threads, one having the producer, another having the consumer, and when they execute at the same time, the thread 2 acquires the lock so that when thread 1 writes the data and then it releases the lock, the printed data in thread 2 is guaranteed to see 100. And without any explicit acquire or release primitives, thread 2 could read stale data. So this is necessary, and this is used in ARM v8 or RISC-V processors. I'm now going to hand the control of this presentation to Reshma for a while. So take it on.
Hi, now I'll be introducing the RTL2 microspec model. Before that, let's quickly get an idea about what is the problem with the existing manual microspec modeling. Manually writing the microspec models for verification is very slow and tedious, and it's prone to mistakes. So this approach makes formal verification inefficient and harder to scale. The solution to this problem would be the RTL2 microspec, which automates the process of generating the models directly from RTL designs. It basically links the RTL designs with the axiomatic microspec models, making the verification faster and more accurate. The main idea of this RTL2 microspec model is that it extracts happen before invariance, the HBIs, that we are going to discuss in detail in the coming slides. So these HBIs are extracted from RTL, which define how the instructions interact over time. These HBIs are then used to by the check tools to verify whether the processor behaves correctly. How does this help? This model basically speeds up the verification process, making it scalable for complex designs. It works smoothly with existing check tools, ensuring thorough and efficient verification of the memory consistent models, which in turn reduces the manual effort. Moving forward, to know more about the background of this paper, let's first try to understand the challenges in MCM implementation. So, as we have seen earlier, MCMs define the order in which the memory operations should happen in multi core systems, ensuring that the process and threads work together in a predictable way. Implementing these MCMs in hardware is tricky because the design has to make sure these rules are followed correctly across all cores and all memory paths. Even tiny bugs in this design can lead to hidden errors that are hard to find and fix. These errors might not show up right away but can cause unpredictable behavior in real world applications. Now, the question is, why do the current MCM verification methods fall short? The answer to this is traditional formal verification methods rely on system Verilog assertions to check the RTL properties. While this approach is thorough, it requires manually writing a large number of assertions, making it time consuming. Also, the complexity of verifying all possible execution scenarios leads to high computational costs, making it difficult to scale for larger designs. So, as a result of all these, many potential MCM bugs may remain undetected or take excessive time to verify, slowing down the overall design and validation process. Let's check out the other testing approaches. And one such approach is the litmus test. Litmus tests are small concurrent programs specifically designed to reveal potential MCM violations. They simulate different execution scenarios to check if memory ordering is correctly enforced. While they are useful for catching errors, they are not exhaustive. What does this mean by not being exhaustive is just because a design passes a set of litmus tests, it doesn't mean it is fully correct. These tests only identify problems, they do not provide a formal proof of correctness. Since the formal verification is complex and litmus tests are very limited, we need a more rigorous approach. This is where the check in tools come in. The check-in tools use formal verification techniques to analyze MCM correctness against the litmus test. Instead of just running the test, they mathematically prove whether a microarchitecture sticks to its memory model. But these tools require a manually written microspec model of the microarchitecture, which is difficult and time consuming to construct again. Now, the biggest challenge is that there is no automated way to convert RTL designs into these microspec models for the formal verification. So, the RTL2 microspec now fills this gap by automating the conversion, making the MCM verification more efficient and scalable. Moving forward, now that we have an idea behind the motivation for actually designing this RTL to microspec, let's see step by step process for creating a complete microspec model. Here, the workflow begins with passing the RTL to identify the state elements and construct the data flow graph, the DFGs, which represents the data flow across the design. Following this DFG extraction, intra-instruction HBIs are synthesized by identifying ordering constraints within individual instructions. Next, structural, temporal, and data flow dependencies between instructions are analyzed to synthesize the inter-instruction HBIs. Now, the correctness of all these synthesized HBIs is validated through formal property verification using tools such as Jasper Gold to confirm the compliance. Once the synthesized HBIs have been validated and everything checks out, the fully verified model is ready to go. Let's move forward and discuss about happens before invariance, HBIs. These HBIs are used to capture the causal relationships between the hardware events. These relationships help in understanding the order in which the operations must occur within a hardware design. There are two main types of HBIs, the intra-instruction HBIs and the inter-instruction HBIs. We will be discussing in detail about all of this in the coming slides. First, let's see why are these HBIs important. The HBIs play a key role in the RTL2 microspec model. In the systematic extraction, this systematic extraction ensures that the hardware behaves as expected, respecting the necessary ordering constraints between the operations. There is an alternate way of expressing this HBIs, that is the happens before graphs, which have nodes and edges as the main components. Moving forward,
We are going to be looking at intra and inter instruction HBIs in a bit more detail with a bunch of examples. So, intra instruction HBIs, they define the execution paths of individual instructions in the microarchitecture. And the role in the microspec models is that it is required for each ISA instruction to accurately represent its ordering behavior. It encodes which hardware state elements. Is it a register? Is it a memory cell? Which is that state element and instruction updates during execution? And it also defines a partial ordering of these state updates, which ensures the structured execution flow. I have a simple example here from the paper. So, as you can see here, there are three HBIs and they have been encoded in a single axiom in the microspec. The HBI 0 specifies that for all instructions I, such that I is a memory read operation, I will update the instruction DX state element before it updates the MG node 0 state element. Similarly, for HBI 1, the MG node 0 is updated before MG node 3, and so on. So this is a simple example of an intra-instruction HBI, and it instantiates the nodes and edges for load instructions. When we talk about inter-instruction HBIs, it gets a bit more complex because there are multiple types. So these HBIs describe how different instructions interact during execution. We have structural dependencies, which have spatial and temporal dependencies, and then we have data flow dependencies. So in spatial dependencies, we ensure that the multiple writes to the same register or memory location are serialized. If you look at this quick example here, this asserts that for all pairs of instruction I0 and I1, if I0 appears in program order before I1, then I0 will update instruction DX state element before I1 does. So this is the simplest dependency to understand. When we talk about temporal dependencies, we have to manage execution order when different instructions update distinct state elements. So execution time is multiplexed across instructions. When we look at this example, this axiom asserts that for all pairs of instruction I0 and I1, and both of them are write instructions, if I0 updates instruction DX before I1 does, then I0 will update MG node 2 before I1 updates MG node 0. So just one HBI is included here, but this gives a great example of what temporal dependencies mean. Then we have the data flow dependencies. So, for example, a store must complete before a dependent load reads from the same memory location. So this is similar to the hazards we have in computer architecture. So in this example, we can see that we assert that for all pairs of instruction I0 and I1, where I0 is a memory write and I1 is a read, if both I0 and I1 access the same physical memory address with no intervening writes, then I1 reads the value written by I0, then a data flow dependency exists between I0 and I1 via the memory. So the importance here is to ensure that loads do not read stale data, and this prevents memory consistency. More importantly, it prevents speculative execution from violating the expected data dependencies. Therefore, by capturing both intra and inter-instruction HBIs, the RTL2 microspec, it can systematically extract the RTL execution rules, convert them into microspec axioms, and then this is the process of automating MCM verifications. Now, Reshma and I came up with a bunch of our own examples to drive home this point of intra and inter-instruction HBIs. So let's have a look at them. For intra-instruction HBIs, consider a store word instruction that writes data from register to memory. The sequence of hardware events will have a decode instruction, read source register file, computing effective memory address, which this ALU stands for, and then writing data to the memory, which is DMEM. So the HBI 0 says that the instruction must be decoded before the source register can be read. The HBI 1 says that the memory address must be computed after the register read. And HBI 2 says that the store to memory must happen after the address calculation. So this is a slightly more trickier example as the one we saw earlier, but this is the simplest instruction HBI to understand. When we consider the inter-instruction HBI, we have a data flow dependency in this example. So consider two instructions I0 and I1 in a pipeline processor where I0 produces a register value that I1 consumes. I0 is an arithmetic instruction that writes to register. I1 is a dependent instruction that reads from that register. The processor uses register forwarding to bypass the register file and directly pass R1's value from I0 to I1, ensuring correct execution. Since I0 depends, my bad, since I1 depends on I0's results, I0 must execute first to produce the correct value. So instead of waiting for I0 to write back to R1 to the register file, the processor forwards R1's value directly to I1, avoiding unnecessary stalls. So the HBI ensures that I1 does not fetch its operand before the forwarded value is ready, and this prevents I1 from using the stale data. I have a couple more examples here for spatial and temporal dependency. The spatial dependency example is a trivial one. So if two instructions I and j attempt to write to the same destination register, their execution must be serialized to ensure correctness. And this prevents race conditions where multiple writes to the same register might occur out of order. This temporal dependency example, consider two instructions I0 and I1 executing in a superscalar pipeline. Even though the processor can issue multiple instructions per cycle, it must retire instructions in the program order to maintain correctness. So if I0 is scheduled to retire before I1, then it must reach the retirement stage first in the pipeline, and only then should I1 reach it. I0 must also update the architectural state before I1 does. And even though I0 and I1 may have executed simultaneously or out of order in earlier pipeline stages, the important point here is that the retirement must happen sequentially to prevent inconsistencies. And this is what this temporal dependency example puts forward. Back to Reshma.
So here, this flowchart gives a detailed description of how synthesizing the microspec model from RTL happens. This is similar to the high-level overview we saw, but in a more detailed manner. Here, it starts with system Verilog or Verilog designs, generating a full design data flow graphs to capture the data flow. The RTL is then transformed into a netlist, which in turn is used in extracting the DFG. The DFGs capture complete data flow information, which naturally represents the happens before relationships. Next, intra-instruction and inter-instruction HBIs are synthesized by hypothesizing and validating ordering relationships using the tools like Jasper Gold. Then the validated HBIs are merged and translated into the microspec format, creating a complete verified model. This is the main idea behind synthesizing the microspec from RTL. Moving forward,
So we are going to be looking at the synthesizing part now, which is synthesizing the intra-instruction and inter-instruction HBIs. The goal here is essentially to determine the order of operations within a single instruction's execution. As we already discussed, we use a full design data flow graph to extract the necessary information, and constructing the FGs need these. It requires user-supplied metadata, such as instruction fetch register, program counter registers, and binary encodings, to name a few. The front-end processes, such as instruction fetching and decoding, completely removed, focus only on the execution. The possible ordering constraints are hypothesized based on a single execution path per instruction, and these automatically generated assertions help encode these hypotheses. And the final step is that these hypotheses are converted into assertions, which act as verification checks for the correctness. So this sums up synthesizing intra-instruction HBIs. Now we're going to look at synthesizing inter-instruction HBIs.
so this process of synthesizing inter-instruction HBIs begins with analyzing the control flow data flow graph, the CDFG, to understand the flow of data and control within the design. Based on the analysis, the HBI hypotheses are generated by considering spatial, temporal, and data flow dependencies as we have seen before. These hypotheses are then formulated into three key system Verilog assertions, which are namely the request sent, request received, and the request process. The assertions are basically used to check these processes occur correctly. Next, the hypotheses are validated using the verification tools, and the formal checks either prove or refute the hypothesis. And if necessary, the invalid ones are reevaluating by inverting the reference order. Once we have a complete set of validated HBIs, the next step is to convert them into a fully structured microspec model. This involves two key processes: node merging and syntax translation. In node merging, RTL to microspec merges state elements into larger nodes, which in turn improves the efficiency by combining the related nodes involved in inter-instruction HBIs. And then these validated HBIs are translated into the final model using the syntactic rules for analysis. Now let's see the case study of a multi-5 scale processor. The design is involves four sequentially consistent RISC-V cores with a three-stage in-order pipeline. It has a shared memory module accessed via round-robin arbiter, and single arbiter serves one core per cycle, allowing pipeline memory access. And it has certain modifications as mentioned here, and the tools mentioned here are used for verification of this case study. Coming to the results of the case study, the interesting part of this is a bug has been discovered in the multi-5 scale. So the issue was an assertion failure where memory requests from same core was not maintaining the correct order for certain instruction pairs. By analyzing the counterexample trace from Jasper Gold, the authors identified the root cause, which was a store word instruction error with an undefined encoding. This encoding was not tracked correctly by the memory logic, leading to the memory updates based on invalid instructions, even though they shared the same request ID. As a result, the memory update was violated and the issue was fixed. The model was resynthesized to address the problem. Coming to the performance of this RTL to microspec model, it showed a total runtime of 6.84 minutes, with a majority of the time spent on evaluating assertions. And optimization in this process involved generating a structural HBI hypothesis by analyzing specific instruction pairs. For example, here load and store, which simplifies the verification process. This specific instruction pairs identified reduces the number of assertions that need to be evaluated, which cuts evaluation time by a factor of I square here, where I is the number of instruction types.
Start.
Coming to the comparison between the RTL2 microspec and the RTL check, the first image here compares the overall verification process, including both the time to synthesize the microspec and the time it takes to evaluate the 56 litmus tests on that model. The second image focuses only on the runtime for evaluating the litmus test, comparing how long it takes to run the test for both RTL check and RTL2 microspec model. Let's move forward.
We are going to look at analysis of this paper now real quick. So the strengths of this paper lie in automation because we are reducing manual effort by automatically extracting microspec from RTL, speed. We are synthesizing this model in under 7 minutes and verifying litmus test in under less than a second. Accuracy. We are using Jasper Gold for formal verification. We are ensuring correctness without heavy simulation. We already found a new bug, and it is really efficient because it simplifies verification by reducing the need to manually write assertions. There are some limitations, such as this only works for in-order and limited out-of-order processors. There is no speculative execution support. This still requires some manual metadata. Most of the time is spent evaluating assertions in Jasper Gold, which slows down large designs. And there is no guarantee that it will catch all errors, and there is no comparison with other tools. So the impact and conclusion of this is that this is pioneering work, as RTL to microspec was the first to automate microspec synthesis from RTL, and this influenced newer tools. It also enabled large-scale hardware concurrency analysis. It drastically reduces the model synthesis time, and unlike RTL check, it allows early bug detection before the hardware is built. It synthesizes a model in under just 7 minutes. And the best part is that it already found a new bug in the RISC-V scales Verilog already. So this concludes our presentation, and we are welcome to take any questions you may have. Thank you.